So guys, very good afternoon one and all. So we are continuing with the topic that we have discussed in the previous class, double integration method for analysis of slope and deflection in a cantilever beam and simply spotted beam and so on continuously. So one of or 2 points we have already discussed, the derivation of double integration method that we have seen in the previous class. Now we are going to see some different problems by using double integration method. You can say different cases. Different cases means the cantilever beam which is under with the different type of loading. So one by one we will see those, and let's try to understand. So first of all, deflection and slope for different load cases. I hope everybody go through the notes that I have already shared in your Google Classroom. Those who are not even bothering about the notes whether they are uploaded or not, please, it's a request from my side, go through the notes and download them and see what are the things that we need to be focused on this particular subject. So first case we are going to look after here, that one case already discussed, I think, that is a point load at a free end that we already discussed in the previous class. We are so I'm not considering that particular once again. So I'm start by the one first case, which is having a cantilever of length L. As you can see, this is a cantilever beam in the diagram. A cantilever beam, we know that one side is fixed end and other is a free end. So length is L, carrying a concentrated load W, that is at mid of the means it is not a mid center, it is W at a distance A from the fixed end. So we need to calculate the deflection at C and slope at C. These are the things that we need to find in this particular problem. So for this particular segment, what we need to understand, first of all, we should know what is the deflection when there is a load at the free end. In the last class, we have seen that, which is I don't have in this particular class. I'm just mentioning that. So we have seen the last case where we have a cantilever beam and point load is acting at free end. At again, the value is W. In that case, we have already seen what is a slope equation, what is deflection equation, and you can say what is a maximum slope and what is the maximum deflection, which is obviously occurring at the free end. And at this end, there will be no slope and deflection because we know that fixed chord does not allow us to move in up and down, and there is no rotation possible. So slope and deflection both will be zero in the case of fixed end. So first of all, what we need to understand here, dear students, from the figure, if you see a cantilever beam ABC, as you can see, this is the A point, this is the B point where the load is acting, and this is the end C. This question was given to you for a homework, but maybe one student only submitted the solution. No other student has been done any work for that particular problem. Nobody sent me any solution other than only one student. Concentrated load, that is W at B distant from the fixed end A. The question was given, that is a cantilever beam ABCD, there is a point load W, magnitude is acting A distance from fixed end. Fine. Now we are supposed to theta B, which be the slope at B, and YB is the deflection at B. So theta B, and this is the theta B here. You can write here, that is theta B, and YB. YB is a vertical distance of deviation. Basically, this is YB. This is your YB or VB, you can write. So these are the values we have. The deflection at B, we have slope B, that is theta B, which is equal to WA square by 2EI. If you remember in the last class, we have seen W L square by, or basically you can write better to write X 2EI. Now what we need to do, we just need to replace the X value as A because we just putting the value of, instead of X, we are getting to put value A, that is a slope at B point, at slope at this B point. And YB, that is a deflection. As we know that deflection in the previous case that we have seen, I should be there. In the previous class, we have seen that is W X cube by 3EI. 3EI. EI. These things we have seen in the previous class. So now what we need to do from this segment, if you see, but let me first explain all the particular things, then I will bring you to the points here. What does that mean? Actually, I want to calculate the deflection, this total deflection here. This total deflection I want to calculate. Fine. So if you see, as we don't have any load between segment B to C, as we don't have any bending moment, obviously load is not there, though there will be no bending moment also. In this particular segment, deflection of this line particularly that remains straight. Up to this extent, it will be a curvy kind of way, or means you can, the curve will be like this. And after the B point, there will be a straight line because there is no bending low moment between the B and C, or you can say, better to say, there is no load. That's why the line is straight enough. So from there, if you want to see, if I want to calculate CC here, C to C1, that is a total deflection which is happening when there is a point load acting a distance from the fixed end. So CC I want to calculate. What I need to do calculate here? I need to find CC2, yes, plus C2, C1, plus C2, C1, C2 and C1. These are the values I need to find first. So what I actually do here, or what I am going to do here, basically I just, I know the value of this Y here, because that is value is nothing but this is the WAQ by 3I. And I know the value of theta B, which is WA square by 2EI. Now what I am going to do, I just put a perpendicular over this particular line on C to C1. I draw a perpendicular. So I can say that this YB will be equal to CC2. YB will be equal to CC2. So better I can write CC1, that is distance I need to find, will be equal to CC2, which is equal to YB plus this C2 to C1, C to C1. If you see this image, this is a triangular shape here, that we know that this is a triangle, and this angle makes angle 90 degree. If I want to calculate this perpendicular, what I need to do, I know that tan theta is nothing but tan theta is nothing but it is perpendicular by base, P by B, perpendicular by base. What I need to find here, I need to find the perpendicular distance. This perpendicular distance C2, C1 I need to find. What I will do, I will cross multiply it, tan theta into B. Tan theta, P is equal to tan theta into 10. I just write 10 only, theta is not writing. 10 into B. 10 into B. Now B I know, which is nothing but L minus A, and theta I already calculated, that is WA square 2E. So what I can do here, YB will be equal to CC2. CC2 is nothing but YB. Sorry, YB is basically YC. I need to write YC. This is YC. That will be equal to YB plus C2 C1, which is perpendicular. Perpendicular is nothing but this slope into L minus A. Slope is, we already calculated, that is WA square divided by 2EI into L minus A, Just do the L minus A. That is all about, that is the value that we need to find. Yes. Similarly, you can calculate the slope also here. If you want to calculate the slope, what you need to do, just do this calculation. Slope will be this much. Directly you can calculate slope remains in this value. So in that's how we can calculate, guys, because there is no bending moment. Due to that, there will be no theta will happen. Theta will be constant after B point because there is no bending moment. Fine. So that's how we are going to calculate in this particular case. So let me clear first all the points. So next case, this case has been discussed in the previous class, but I just want to, I should explain again. So that's why I just bring, but I will not take more time to discuss this particular point. So in this case, what we need to consider here, that is, we are considering a cantilever beam of AB. A is the fixed end, B is the free end. Of length of the span is L, which is fixed at spot A and free at B, as you can see in the diagram also, with uniformly distributed load as displayed in the figure, as you can see, everybody. So a cantilever beam is there. A is a fixed end, B is the free end, and there is a UDL loading over the entire span of a magnitude of W Newton per meter. So in this case, if you see, this is a deflected shape, as you can see in the diagram by particular this line. This is the deflected shape. I want to calculate this y and the slope at the b end. That is the thing that we need to find by using the double integration method. So first of all, what you need to do, dear students, we have to consider a section. So here I am cutting a section which is far from the end A of distance x, and make a free body diagram of that segment. So free body diagram of this segment definitely will be like this only. Yes or no? Yes, it will be like this only. So before doing either of the way, you can cut the section from this end, or either you can cut the section from this end. This is your choice. No force from my side. You have to consider from that end only. I just mentioning in the previous case, we consider from this end. So I want to try to explain, if you consider from that end, there will be no change in the slope and deflection at point B, but the condition of boundary, like from where you are considering the x instead of x, is you need to put 0 or x equal to L. In that case, deflection slope will be 0. According to that, I just try to emphasize something new for you people. So better you should know from the both. And if many times people in the exam, it will given like this only. So in that case, how you will solve that problem. So that's why I'm just considering x from the fixed end. So otherwise, for being a simplification, always take a section from the free end, because we do not need to calculate any support reaction before cutting a section. Okay. So what are the things those are mentioned here? W, that is the rate of loading in Newton meter, has been given. Yes, we can see this from the figure. AB is the position of the cantilever before the loading. Yes, before loading, beam will be straight as it is shown in the figure A to B. A dash B, A B dash, that is deflected shape. Position of the cantilever beam after the loading. After the loading, this is the deformed shape of the beam. This one. This is a deformed shape. Theta A, slope at A, fine. Theta B, slope at B. At this end, if you extend it and draw a tangent like this one and make a horizontal with it, so this angle is your theta B. YB, deflection at free end. This is the YB, that is a deflection at B. And the total load due to the UDL, obviously, if you convert into the point load, that will be W into L. So you can write it as capital W, which is equal to small w into L. Small w, intensity of load in the UDL term. So you can convert into the point load also. Now, if you see the boundary condition means the known point where we know the slope and deflection before solving this problem. So we must aware with the boundary condition applicable in such a problem where beam will be cantilever beam with the UDL. We have following boundary conditions mentioned under. What are those? At point A, we know deflection is 0 because there is a fixed spot which is not allows to beam to deflect downward. At point A, slope is also 0 because the fixed spot is again not allow us to rotate. At B, the deflection will be maximum, as you can see. And the slope at B also maximum at this point, because exactly here if you draw the tangent, as you move towards a fixed end, slope value and deflection value will be reduced. So these values you should know before starting solving this problem. So let's go to the next slide. So what we need to do now, we have to cut a section or consider a section and calculate the bending moment at that point. So as I mentioned in the previous slide, let me draw here also. I consider the section from this fixed end. So this portion we are considering. So what you need to do, you have to cut a section, make a free body diagram. Free body diagram will be like this only. Yes or no? It will be like this. So we need to find the bending moment first. Bending moment at this fixed end cutting portion, means at a distance x from the fixed end, at a distance of x from the fixed end. What is the value of bending moment? M of x will be equal to the reaction will be equal to how much? What is the value of reaction? Reaction will be WL by 2 or capital W by 2. Yes, W, small w, if you take a UDL instantly, in that case you can write WL by 2. WL by 2. I'm just taking WL by 2 here. This is the reaction into x if you take a section from this end. Fine. If you take x from this end, or that distance obviously coming out to be L minus x. If you consider x minus L x in this case, so that will coming out to L minus x. This will be x only. In this case, if you consider x from this end, so I just writing the equation of movement in case of x we are considering from this end in this particular case. So let me put first complete value. WL by 2 into x minus your bending moment. Your bending moment, what is the value of bending moment? That will be W into L. That is a point load acting at the center. What is the distance remaining? WL into L by 2. So WL square by 2. WL square by 2. WL square by 2 into will not be there. WL square by 2. That is the value of bending moment. From the fixed end, if you consider. And if you consider from free end, if you consider from free end, in that case, this is the section from other end. If you consider, in that case, this is the value of W. So in that case, first of all, convert into the point load. W into x, or x is nothing but L minus x only. L minus x into XL. L minus x means length by half by 2. That will coming out to be Wx. W by 2 L minus x square. So let me first. So after writing the bending equation, what we need to do integration first and add the integration constant C1, and then again integrate it. After second integration, what you will get? WL minus x power 4 divided by 6 into 4, that is 24, plus C1x plus C2. This is the value of Journal's deflection equation with the constant of integrations are there, C1 and C2. To calculate C1 and C2, what we need to do? We have to put the boundary condition to solve C1 and C2. So where C1 and C2 are the constant of integration, we can secure the values of these C1 and C2 by considering just apply the boundary condition that we just going to put. So what are the boundary condition? As we have considered the x from the fixed end, I just mentioned the slope will be 0 when x is equal to 0. Why? Because x is equal to 0 means we are at the fixed end point. dy by dx will be 0. And x is equal to 0, y is also 0, means deflection is also 0 because we are at fixed point. By putting x is equal to these values, we will get the value of C1 and C2. As after applying the boundary condition in the above these two equations and C1 and C2, what you need to do? Dy by dx will be 0. X, just put value for x is equal to 0. So by doing so, you will get value of C1 is equal to WL cube by 6 and C2 will be WL 4 power 24. That's how we will get the value C1 and C2. But after, what we need to do? You just need to put the value of C1 and C2 in the equation of slope and equation of deflection and solve further. After putting all the values, as you can see in this case, but we will get just we need to find, these are the general slope and deflection equation. Now we have to calculate where we need to calculate the slope and deflection. We want to calculate a deflection and slope at free end, but we have to do, we just need to put the value of x instead of x, we need to put the value of L. Similarly in this case also, so that become 0, and ultimately we have to get these values. After solution you will get value theta b, which will be equal to WLQ by 6CI. WLQ by 6CI, and deflection will be minus WLQ by minus WL power 4 by 8EI. These are the value we will get after putting all the values into the equations. That's all about this particular. So next we have a different case again, a new case. Deflection of a cantilever beam with uniformly distributed load for a distance A from the fixed end. A cantilever beam, as you can say, the next case is a deflection of a cantilever beam that we need to find a uniformly distributed load acting a distance from the fixed end. So what is the given data here? So A and B is the beam it's given, C is the center point, or you can say the UDL loading is at A segment. It is the same problem as we have discussed in the first case of where the point load is acting distance A from the fixed end. The similar approach we are going to apply here also. What we need to do here, dear students, the same thing that we have did in the previous segment. The total deflection we already calculated in the previous case when the UDL is entire span. What was the value? Value was WLQ by 6EI and WL power 4 by 8EI was the slope and deflection values. Now we have to get those values for point C. Means again the deflected curve up to the C segment, it will be in like a curve. After the C point, it is a straight line. Why so? Because there is no load between the segment C and B. So what we need to find, we have to draw the perpendicular from the C and that B to this line up to this particular point. Wait. Up to this particular point, that distance will be same. So I can write theta C will be equal to WAQ by 6CI. YC will be equal to WA power 4 by 8EI. These are the values. Yes, we know that. Since the portion CB of cantilever is straight, therefore slope at C will be equal to the slope at B. That I already know, because after C point there is no load, slope will be the constant after that segment. Whatever the value we have, that remains same. So theta C equal to theta B will be equal to WAQ by 6CI. Now I am interested to calculate the B to B dash. B to B dash, that distance is nothing but will be equal to YC. And this distance from this particular point up to this particular point, if you want to calculate, this is again our 90-degree angle triangle. Again, we can solve the same approach as we did in the point load case. So theta C, we know we need to get the perpendicular value that will be equal to base into the theta C. Base into the theta C into the base, as you can see here. Just put into the values. That's how we can get the value of slope and deflection in the case of any low UDL load of a distance from the fixed end. Next case is when the UDL is from at a distance of A from the B end. In that case, I'm just going to explain the things. Those is very important. Otherwise, everything is mentioned here that I'm not going to explain this particular. So what I'm going to explain is this diagram, which is very, very important. So dear student, if you see in the previous two slides, first that we have considered completely UDL part. Yes, we have considered that. Second segment, we have considered the UDL A distance from fixed end. Fine. Now, if you see from this particular diagram, what you able to see or what you able to understand is this is the deflected shape. As you can see, the W is unit length from the C to B, means it is a distance A from the free end it is acting. And we have seen in the previous case, first case of UDL and over the entire span. And we have seen the UDL case when the UDL is in A distance from the fixed end. Now, what is the conclusion here? If I able to calculate the value of UDL in the entire span UDL over the entire span, In that case, what is the value of deflection at B and what is the slope at B, that we know. That is, the value is nothing but WL cube by 6EI and WL cube by 8EI was the values. Fine. Now the point is, if it is the UD load at this end, so let me draw in the complete over a single beam. So you will better understand what is the point which I am trying to say here. And one is, let me take the other color so you will better understand this. This is the complete story, dear students. But I'm trying to explain, we already seen the red color UDL means the entire over the entire segment. What was the value? Value is WL cube by 6CI, the slope, WL 4 by 80I was the deflection. And we know the value of deflection due to this load also. That was a downward side. We can take on upward side, there will be no issue. But I'm trying to say, if I want to calculate the effect of this green one UDL, which is at this distance, which is the question is all about. If I minus the effect of this load from that completely and UDL over the entire span, what I will get the effect of this load. Yes or no? I will get that. I will get that. So next we have a case of deflection of a cantilever beam with a gradual varying load. Now, what we need to do, we have to calculate the deflection due to the gradual varying load. What we can do in this case, the same thing that we have done in the UDL case, you have to cut the section, calculate the bending moment, put into the bending EI d square V by dx square, and integrate one, you will get slope, and integrate twice, you will get the deflection. What you need to do, you have to cut a section, as you can see from there, as it is cut the section here. You can take this portion to be X. In that case also there is no issue. If you are considering X from this end, so that will be obviously L minus X. So if you want to write, first of all, the issue is, what is the value of this vertical distance? By the similar triangle, everybody can calculate that this distance divided by the total one, this base divided by total base. So this length will coming out to be L minus X by 2. L minus X by 2. That's how you will get the value. Fine. So let me consider that particular. Consider a X at a distance X from that A. The load at X will be W L minus X per unit run, means W by L minus L by X, obviously. Hence the vertical height we need to find, the vertical height at this end, that we need to find W by L minus L, L into L by X. Hence the bending moment at this section will be, अगर मैं इसको B लेता हूँ, let me calculate for you people, might be you are not able to. So B by W is equal to, if this is L minus X, L minus X, L minus X, sorry, L minus X is there, divided by total length, that is L. So that will be coming out to be W L minus X by L minus X by L. This is the value of that vertical distance or vertical height at point B. Fine. This the height we need to find. I just do the similar triangle concept, nothing else. So this height we have. Now we need to find the value of moment. If you cut the section and draw the value, like this is the value. What is the height of this segment? That is W L minus X by L. L minus X by L minus X by L. This is the value. Now we need to find the bending moment. That will be nothing but area of this triangle, half base is L minus X, L minus X, X if you are taking from the fixed end, L minus X base आ गया, into the height is, this is the mention already, H is W L minus X by L. This is the area. Now it will act at the centroid. It will act at the centroid. What is the distance remaining? That is 1/3 of L minus L minus X, L minus X. So this is the complete value. As you can see, area half W L minus X into L minus X by 2. So basically this value is coming into half of 1 by, this is the area, this much is the area. Base half, base is L minus X into W by L minus X. This is the area into, it will act at the centroid, and centroid distance to this end is 1/3 of L minus X is equal to, this is the value of bending moment will come. Now these are the value you have to put into the double integration equation. That is nothing but bending moment at any section is given by M is equal to EI d square y by dx x square. Put the value of bending moment here, integrate once, you will get the value of slope equation, you will get the deflection equation. Now we have to find the C1 and C2. We know the boundary condition again. C1 we need to find in the first case. If you consider this x will be equal to 0, in that case C1 we need to find, means dy by dx will be 0 when x is equal to 0. Y is also 0 when s is equal to 0. These are the values already mentioned. So where C1 and C2 are the constant of integration, their values are obtained from boundary condition. As we know that x is equal to 0, x equal to 0 means we are at fixed end. Y is equal to 0, that deflection at fixed end will be 0. X equal to 0, slope will also 0, because at a fixed end slope and deflection both will be 0. Dy by dx 0. By substituting x is equal to 0 and y equal to 0 in the equation 2, we will get the value of C2. C2 value is coming out to be WL4 by 120. Likewise, x is equal to 0, dy by dx means slope will be 0. Put the value of in equation 1 and we get the value of C1. So that will coming out to be minus WL3 by 24. Now we know the value of C1, C2. Again, re-put into the equations of slope and deflection of C1 and C2. These are the values: W by 24 L minus X power 4 minus WL3 by 24. This is the value of C1. C2 and C1 value put into the general slope deflection equation, that is minus W by 120 L minus X power 5 minus WL3 by 24x plus WL3 4 by 120. This is the value of C2. Now wherever you want, these are the two general equations which are important one. These are the two required equations we have prepared here. Now just you need to put the value of x wherever you want to find the slope and deflection. Wherever you want the slope and deflection. So just after doing all that stuff, you can get the value of theta b, that is coming out to be at free end. That will be minus WL3 by 24 EI negative, means it is in clockwise direction, and the YB is also coming into the negative WL power 4 30 EI. That is again downward direction. That's why the sign is coming out to be negative. So that's all about this particular segment or particular case.